Okay, so we're working on hypothesis tests for a population proportion. We're testing claims for a population proportion. So the example is as follows. In a random sample of 1,100 voters, 516 say they'll vote for the Democratic candidate for president. We want to test the claim that a minority plan to vote for her using a 5% level of significance. Okay, so the gathering of sample data is our first step. So you'll need to gather, this is easy step here, you'll need to gather p hat, which is x over n, number of successes divided by sample size. You'll obviously need the sample size. You'll need alpha, which is called the level of significance. Now, just to remind you, statistically significant events are rare. With low probability. Okay, alpha is your rule for how probable a statistically significant event should be. And maybe I'm going to say improbable. Okay, that sounds better. Okay, so yeah, it should be a low probability. So I think in parentheses, I'll just add like a 0.01 to 0.05 usually. Okay. And you can do bigger, so 5%, if you do a 5% level of significance, you're just saying anything with a probability of 5% or less would be considered statistically significant. And so basically you're sort of making the rules of your game when you do this. You're saying, well, I'm going to believe my event is significant if its probability is less than whatever your level of significance is. So for the example, our p hat is x over n. So there's 516 successes here out of 1,100. And with proportions, we always do 3 places. So I should say 3 significant digits. So what do you say, guys? Should be 0.469. Okay, now they're saying that a minority plan to vote for the candidate. And what you're observing here is a minority, for less than 50%. Okay, so this seems to be supportive of what they're saying, but we're worried that it's just a kind of chance fluctuation. Remembering that statistics from samples are not that reliable. We have to think about how, basically this thing can't be within the margin of error of 50%, which is the cutoff for a minority. You have to be less than 50% to be a minority. Okay, so yes, this is less than 50%. That is a minority, but is it within the margin of error? That is to say, is it statistically significant in terms of how much less it is less than 50%? Okay, any questions? So we kind of have to see how many standard errors it is below 50% before we say that it supports, because if it's not very many standard errors, that's just margin for error. Okay. All right, our N is obviously 1100. Our level of significance, alpha, is up here, it's 5%, so 0.05. Any questions yet? Okay, then it says to identify the null hypothesis and the alternative hypothesis. These are claims about the population proportion. Null hypothesis is abbreviated HO. Alternative hypothesis is H1. Again, these are claims about the population proportion. We assume the null hypothesis is true, but we will try to prove the alternative. Also, we'll check the conditions for normality here. So in general, the null hypothesis says that P is equal to some value. Okay. The alternative hypothesis has to be one of the three that I'm listing. Okay. It either says that P is less than the same value, or P is greater than that same value, or P is just not equal, and not equal means less than or greater than to that same value. You have to pick one. Okay, and then once that's done, you have to, the check that comes in is that NP has to be at least 10, and N times Q has to be at least 10, okay? And you get P from the null hypothesis. Remember, we assume the null hypothesis is true. It's like a jury trial where you assume somebody's innocent, but then you try and prove they're guilty. That's exactly what we do here. Okay, so get P from the null hypothesis, which we're assuming to be true. Okay. Any questions? Now, I would recommend you do HA first, so it's easiest. Okay, so let me show you what I mean. I'll just put HO. It needs to say P is equal to some value. And then HA will say AP is less than, greater than, or not equal to that same value. Okay, so I'll put the P down here, but next thing I have to do is less than, greater than, or not equal. Now, this is the claim you're trying to prove. If you look here, it tells you the claim. It says test the claim that a minority plan to vote for her. A minority is Less than, greater than, or not equal to what value? Anybody?
Would it be less than?
Less than what?
Than the claim,
What proportion or percent is a minority?
5%.
Try it again.
50.
Yeah, 50%. So they're saying less than 50%. That is their claim, meaning she's going to lose the election, right? Less than half. Any questions? So the claim is that her proportion, her population proportion will be less than 0.50. So we want to know if she's going to lose. Okay. Now we won't know for sure, but we can at least look at our evidence and see what it supports. Okay. Now the null hypothesis, you actually need a value for the population proportion. So you actually assume it's 50%. And then we're going to see how many standard errors below that we get. Okay. So the null hypothesis, you have to use the same value here. Okay, so you put in a 0.50. This is what we assume to be true. But the alternative is what we try to prove. Just like, again, in the jury trial, you assume the person's innocent, but then the whole trial is about proving guilt. And for us, guilt is the alternative hypothesis. Any questions? Now the check, you use the P from the null hypothesis. So NP is, N was 1100, I think, somewhere. Yeah, N is 1100. And then we're assuming P is 0.50, which is half of 1100. I think that's 550. And this is the thing that has to be at least 10. And then NQ, 1100. And then down below, reminding ourselves Q is 1 minus P. So this is obviously 50, it's a 50-50 thing, right? So 1 minus 0.50 is 0.50. Okay, so P and Q are the same on this one. So these both come out to 550. And of course, both are greater than or equal to 10. Any questions about that whole process? So again, the margin of error is always about 2 standard errors. So the whole testing process is just to basically say, yeah, we're saying she's greater than 50. We're trying to prove that she's less than 50%. But the margin of error is within 2 standard errors of whatever your statistic is. So whatever statistic you get, it needs to be more than the margin of error below 50%, because that statistic is not that reliable. Okay, it will have 2 standard errors in the margin for error. So to prove this, you've got to be about 2 standard deviations below. Any questions? Does that make sense? And to be 2 standard deviations below is what, and when I say 2, I mean about 2 standard deviations below. And that'll be statistically significant if we can pull that off. Okay, any questions? All right, so now we just need to count how many standard errors that the sample statistic is from 50%. Okay, so the test statistic, is just our z-score. So the z-score is always value minus mean over standard error. Okay, so let me move that down a skosh. So the value is going to be our p hat. to see how many standard errors it is below the mean. The mean of sample proportions is the population proportion. This has been a while since we've seen this. And the standard error of sample proportions, that's called sigma p hat. So the standard error is the square root of PQ over N. Okay, so that's all sort of old information. Okay, so you're just doing P hat minus P over the standard deviation, which is the square root of PQ over N. Okay, any questions? Okay, so this counts how many standard errors that P hat is below from P, let's say. So that'll help us determine if it's significantly less than 50%. And that's important again, because if it's not, then it's within the margin for error. And if it's within the margin for error, then we don't know anything. I think you like to know, but statistics is also, it's all about quantifying how much you don't know. Okay, that whole margin for error. Trying to be real precise about what you don't know. Okay, any questions? Okay, so this test statistic, we usually abbreviate TS, just FYI, because you're going to see that in a lot of the diagrams and stuff that are in the notes. And in the book too, I usually abbreviate test statistic TS just to keep it brief. We write it so many times. Okay, so let's go ahead and do our test statistic here. Z scores are for proportions. T scores are for means. We are not doing means, we're doing proportions. So again, P hat minus P over square root of PQ. Oops, so try that again. Square root PQ over N. So the P hat, I don't remember, 0.469. And then for P, we're using 0.5, 50%. If you want to put 0.50, be my guest. And PQ is 50-50, 0.5 times 0.5 over N, which was 1100, I think. Okay, so see what you get there. And if somebody could just shout that out when you get it, that would be very, very helpful.
I got negative 2.056.
Good. I'm going to round that to 2.06 if you don't mind. Okay, any questions there? So that looks statistically significant. We can say that the 46.9% from the sample is more than 2 standard errors below 50%. So I think this is supporting. Okay. But we have to compute the probability of getting something this low, because remember, this whole thing revolves around this thing called the level of significance, which is the probability of a significant event. And we said it was 5% is our probability for a significant event. So the question is, well, how probable was this? If it's less than 5%, then we'll call it statistically significant. Okay, any questions? And significant evidence is what you need to prove whatever claim you're trying to prove. Okay, any questions? All right, now the next thing is there's a critical value on the bottom row of table A2. We have right-tailed tests, left-tailed tests, and two-tailed tests. So first of all, a critical value is the number of standard errors required for statistical significance. This is actually not really important yet. I'm going to make you do it anyway, because later on you have to. This is the only way to do it with critical values. There's two ways to do these tests, and right now I'm going to make you do it both ways. One way is with the critical value, and the other way is with the p-value. They're equivalent methods, but one uses basically a z-score to make a decision, and the other one uses a probability to make the decision. Okay, so you have to, I'm making you do both of these, and I'm sorry about that, but they're both important. Okay, so critical value is the number of standard errors that's required for statistical significance. Okay. If you go to table A2, this is where we're back to degrees of freedom again. Okay, but you just go to the bottom row where it says large. That's where we're doing z-scores right now. Whenever we work with proportions, we'll be using z-scores. Okay, so again, this is the bottom row. Here. Okay, then your alpha has to be under 1 or 2 tails. Here, like this. And this is CV, critical value. The number of standard errors required for statistical significance. Okay. So it depends on whether you're trying to show that something is less than a value. If you're trying to prove that the proportion is less than a value, then your sample proportion better land in the left tail of the distribution. Okay. If you're trying to show that the proportion is bigger than a value, then your sample proportion better land in the right tail of the distribution. Okay, now the third case is when the alternative hypothesis, and these all depend on H1, the alternative hypothesis. Did I do an HA? Please tell me I didn't. Okay, so this is going to be something I have to not do. So did you guys see in the notes where it says H1 back here? And I used an HA. If I do that, I'm sorry. This is a different, I'm using a different book than what I usually use on my other classes. So here it should be H1 for the alternative hypothesis. And unfortunately, I have to go back and correct all of these. So I'll do it in red, actually. so you can see my corrections. So this is an H1, H1, H1. Okay, am I good? I think those are the only ones. I teach a different class during the week and it's HA. So I'll please, if I do that again, you'll know, but I'll try not to do that again. Any questions? H1. Okay, so it's H1 that decides what kind of test you're doing, right-tailed, left-tailed, or two-tailed. And you kind of think of H1 as just being an arrow that points to the tail. Okay. To prove that your proportion is greater than a value, again, your statistic needs to land on the right of the distribution. So that's all. So let's go ahead and do our problem here. On table A2, to the bottom row for degrees of freedom, large z-scores. This time our alpha is 0.05 and it's one-tailed. Okay, so take a second. I think that's at the back. If you look, you'll see that's, there's a bunch of tables here. The 13th page of the handout has table A1. The 14th page has table A2. That's what we need right now. Going to be kind of hard to see, but on the top here, we're doing a 0.05 one tail. So that's in this column. Maybe you can see that. And then all the way down to the bottom row where the z-scores are. So I'm going to kind of zoom out on this and draw that all the way to the bottom row. And you should see 1.645 there. So that's actually really easy to pull off. You only need 1.645 standard errors to be considered statistically significant. And we got 2.06, I think. Okay. Any questions? $1.645. Now, we have, oops, did not mean to do that. Hang on. Okay, so this on the table says 1.645. Oops. And then maybe we'll draw our little bell curve here. This is a left tail test on the normal distribution, so we use a z. Okay, z is centered at 0, and 1.645 is the number of standard errors to be statistically significant. Because it's a left tail test, notice how on the left tail test, we make the critical value negative. Makes sense. So whatever you look up, you need to make it a negative, this time negative 1.645. Okay, and the probability of getting something that low or lower is 5%. So that's our alpha equals 0.05. So again, the probability of getting something that low or lower is 5%. That is the area of the tail that we looked up, the one tail that we looked at. So anything that goes less than negative 1.645 has a probability less than a 5% chance of happening and is therefore statistically significant. Okay. So on ours, our z-score was z, I think we said negative 2.06. Okay. And this is in the tail. which means it's significant. Any questions there? Which means we're going to, once you can say your evidence is significant, that means you're going to be able to support your claim. And so we're at a point where we could already make a conclusion here. Okay, any questions? We could make a conclusion, but as I've said, there's two ways to do these problems. One with this thing called a critical value, which tells you how many standard errors you need for statistical significance. The other was with the p-value. The p-value is the actual probability. Notice what I got here was a z-score of -2.06. It's less than 1.645, which means its probability is less than 5%. Okay, but I haven't actually said what the probability is. I just said it's less than 5% because it's in that tail that's a 5% region. Okay, so I haven't said what the probability is. So to be more explicit, you can determine the probability, which is called a p-value. You've seen that term in the book before. Now it becomes a term we'll use constantly. Okay, the p-value is the probability of getting a test statistic at least as extreme as the one we have. So we got a -2.06. That's in the left tail. So the p-value is going to be the probability of getting something that low on a left tail test. Okay, if it's a right tail test, then you have to do the probability of getting higher than that. Okay, if it's a two-tail test, technically what happens on a two-tail test is you're saying, well, I want to know the probability of getting into either tail. So what we usually do is we find the probability for one of the tails and we double it on a two-tailed test, which we'll do after the break. Okay, but right now we're doing a left tail test. So let's just do our probability. This is table A1 for probability. So let me just show you this real quick. So let's draw the picture. Like that. Okay, our z-score was -2.06. The p-value is the probability of getting something at least as extreme as that, which means that low or lower. Okay, so this tail right here is our p-value. Okay, and then if you go to table A1, this is the very first probability table we learned. So you'll have to think back a little. For our z-score, we want to go back to -2.0 and out to 0.06, like that. Okay, so look it up on table A1. On the negative side, let me see if I can find that table. Here. So -2.0 is here. 0, 1, 2, 3, 4, 5, 6, I think is that one. So this is the probability of getting a statistic as extreme as we did with the assumption that the null hypothesis was 50%. Sorry, that the population proportion is 50%, which is the null hypothesis. So there's only basically a 2% chance of getting something this low if the null hypothesis is true, and yet we did get something that low. It's so unlikely that we did, it's statistically significant, and I doubt that the null hypothesis is true now. So I'm going to reject it. Okay. When this p-value is less than the level of significance, you will reject your assumption and say, okay, I proved the alternative. Proof is too strong a word. I've got good evidence for the alternative hypothesis. Okay, again, it's 0.0197. Let's go back. Okay, so that's less than the 5% rule for statistical significance. And that's all you need to do to prove what you were trying to prove, which is the alternative hypothesis. Okay. So make a conclusion. It says if the p-value is less than the level of significance here, which happens when the test statistic lies in a tail beyond the critical value, we'll reject the null hypothesis in favor of the alternative. Otherwise, we fail to reject, but we never support the null hypothesis, and then we have to make a conclusion in plain language. Okay, so the p-value was 0.0197. Okay, this is less than 0.05, which was our alpha value. Okay, less means reject the null hypothesis. And support H1. And then I like to write down what H1 said. It said that the proportion of votes that the candidate's going to get is a minority, which is less than 50%, like that. And then this part here needs to be translated in plain language. And talk about H1 only. So only discuss H1 because HO can't be proven. I mean, the only way to prove the null hypothesis, which says something very precise, the null hypothesis, if you go back, said that the population proportion is 50%. You can't know that unless you survey the whole population. And what are the odds that it comes out exactly 50%? It's just not, it's not going to be 50%. So this is unprovable and probably couldn't be true anyway. There's no point in talking about it. What we have shown is this in this test of significance is that our sample proportion is significantly less than 50%, which means we're pretty sure the candidate's going to lose the election, at least if it was held right now. Okay, any questions about this? So to say this in plain language, we always need a caveat because remember, when you work with data, you are sometimes wrong. A caveat is basically a backdoor where you say, well, I'm pretty sure. Okay, I cannot promise you, but the probability supports the following. Okay, actually, I don't say the probability. We blame this on our data because it was the data that led us to our conclusion. So our data, these values are in support of the claim. And this is where I've used the word support here. Instead of H1, I said the claim. Okay, support the claim. The only thing I really threw in was it's the data. So what was the claim? Less than 50%, right? So let's just say that this candidate, oops, has a minority of the vote. Okay, let's go ahead. I know we've gone long and I'm so sorry about that. We need to take a break. So let's go till 10:15. And we'll do another example. And save your questions up. I'll get those after the break. So I'll talk to you guys in a few minutes.
It's 10:30 already.
Oh God. Okay, so Wow, my clock is so far from here. So how about we say 10:45? Oh, that's too bad. All right, 10:45. I'll see you guys soon. Okay, so we're just going to do another example of this hypothesis test about a population proportion. So we'll go ahead and just read through this real quick. It says, an article claims 20% of college students believe aliens have visited the Earth. I totally believe it. You don't believe it. So you're going to try and disprove it. You randomly gather a sample of 850 college students and find that 190 of them believe in aliens. Let's test your belief at 1% level of significance. So see, you're trying to disprove 20%. Any questions? So you need something that's significantly different from 20%, but you're not trying to prove that it's, I mean, you could prove that it's bigger or less than to disprove this. So, and I don't know any more about your beliefs, so we're just going to try and disprove it. Okay, so the data are, we need that p hat value, which is our x over n. So it looks like you got 190 out of 850. So if you guys don't mind helping me out with these, I'd deeply appreciate it. And if we could do it, you know, without too much delay.
0.223.
5, right? So let's go 0.224. Obviously, our n is 850. Our level of significance, you can see up here, is 1%. I think that's all we have to do there. Okay, any questions? Now, the null hypothesis will always say p is equal to a value. Haven't figured out what it is. The alternative will say less than, greater than, or not equal. Now, again, we're trying to disprove that it's 20%, which means you think it's not 20%. You guys follow me on this? So what should I use here? Less than, greater, or not equal? Anybody?
Less than or equal to?
Now, when they say disprove, wouldn't be greater?
Not equal to.
Ah, there you go. Greater or less
Not
is
equal to.
disproving. Yeah, there you go. So you do an equal sign with the slash. So not 20% is disproving it, but we assume it is 20% until we have evidence otherwise. Okay, so those are our hypotheses. The check, all you have to do is NP, and you get P from the null hypothesis. So N was 850. P, we're using 20%. This needs to be at least 10. Okay, anybody?
170.
Great. And Q is 1 minus P. So this is 1 minus 0.20, which is 0.80. So when you do NQ, this is 850 times 0.80. So what's that?
680.
Awesome, thank you. Okay, so these are both greater than or equal to 10, which is, these are the lengths. I don't know if you remember, these are binomial experiments, and the probability distribution that's behind all of this is really the binomial distribution. And the binomial distribution needs to have tails at least 10 in length so that they taper off on both sides and it makes a bell shape. This is a prior discussion. We have verified that the tails are much more than 10. So this will be a nice bell curve. Now the test statistic is our z-score. Remember, our z-score is the p hat minus the assumed value for p over the standard error, which is the square root of pq over n. Okay, so our p hat is 0.224. The p is 0.20. These are different. I don't know how significant it is. And so the square root of PQ, that'll be 0.20 times 0.80, okay, over N, which is, I think, 850. So this is a difficult computation. I'm going to go ahead and show you what I would do. I think these are among the harder computations that we've done. So I'm going to go ahead and share my Desmos screen real quick. So one moment while I bring that up. Okay, so hopefully you're seeing Desmos. Let me go into the graphing calculator. Just to, if you have trouble making a computation like this that has a really complicated fraction, start by just doing the slash for a division, and that creates a fraction that you can type into. So the numerator obviously is 0.224 minus 0.20, and then a down arrow to make the denominator. And then in the toolbar that you pull up from the bottom, there's a square root function. And in the square root, you want another fraction. So again, you type the slash key, and it'll build a fraction, and it's 0.2 times 0.8. And then in your denominator, you get that sample size, which is 850. Okay, you should get your z-score there. Does that look like what you guys got? I got 1.75-ish. That sound right, you guys? Are you able to do that?
Yes.
That's what I got.
Okay, fantastic. So make sure you can do this computation. I don't think there's much out there that's easier than Desmos for doing computations like that. So if that's your tool, then make sure you practice with it. I'm going to go back to the iPad real quick. Okay, so again, that's what do I say? 1 point, I've already lost it. 1.749. I'm going to go with 1.75. And that's all you have to do there. Okay, any questions? So this one's looking less significant than the last one. We're 1.79 standard errors different from 20%. And the problem with that is that this 22.4% is only 1.75 standard errors from 20%, which might be within the margin for error on this one. So all of a sudden, this doesn't look very significant in terms of how different they are. But the next step tells us how many standard errors we need for statistical significance. So here, I want to remind, just to verify, with this alternative hypothesis, not equal means less than or greater than. So if you go back to the previous page and just remember at the top of the previous page, these are two-tailed tests, okay? Because not equal means less than or greater. And your, wait, let me go to here. Your p-value, because you're counting both tails, you could go into either one. The probability of going into either one is twice as big as the probability of just going into one. So what you end up doing is you double twice the area of the tail. Okay, so that's how we're going to do that p-value. And the critical value, again, a two-tailed test happens when you say not equal. Okay, with the critical value, you have to do plus or minus because you could go in either direction. Okay, to prove this. So where am I? Right here. So let's go to this again. It's table A2. For degrees of freedom, we remember this is a Z distribution problem. So we just say large Z. Okay, our alpha is 0.0, don't know, I think it was 0.01. Yeah. This is going to be just impossible to prove on this one. 0.01, make sure it says two tails this time, like a confidence interval. Okay, because maybe make the note up here. Under the alternative hypothesis, this one's a two-tail test. Okay, make sure you see that not equal means less than or greater, which means left tail or right tail, which is twice as probable. So it's a two-tail test. Coming down here, we can get our Z-score. All right, so I'm going to pop over to table A2. Take me a second here. There it is. I'll erase what we did last time. Again, it's a 0.01 two tails. So this is in the very first column of the table here. Two tails. Okay, all the way to the bottom where the Z-scores are. The rest of these are T-scores. We don't want those. So you can see what's required with a small alpha. It requires high significance. So 2.576 standard errors are statistically significant in this case. It's just going to be really hard to do. Okay. Any questions? So again, it's 2.576 standard errors. That's what's required for significance. I'll draw this. Again, it's a two-tail test. So technically, this could go into either tail of our distribution. But it's way out in the tail. So 2.576. And on the other side, negative 2.576. What's the probability of going into either tail? Well, it's alpha over 2 plus alpha over 2. Okay. Where alpha is 0.01. So there's only 1% chance of going into one of those tails. And if it happens, it's statistically significant. Any questions? Okay, now, when you look at our test statistic, it was 1.75. So that's not even close. All right, so let's just go ahead and put that on here. These are called critical values. You have a positive critical value and a negative critical value. Those are the rule for statistical significance. What we got was like right here, our test statistic was Z equals, I think we said again, 1.75. Okay, so it's not significant because it didn't make it out to what we said it had to be. Okay, any questions? Now, the p-value is the probability of getting 1.75 or more standard errors. So for the p-value, what you do is you draw another bell curve and you plot your 1.75 on here, which is your test statistic. So we'll just put our 1.75 down here. Okay, find the area of the tail here. Lots of ways to do this, okay? But if you go to table A1 and you go for your Z-score, you go down to 1.7 and then 0.05. Looking for it. Here we go. So So 1.701, 2, 3, 4, 5. It says 0.9599. But that's the area to the left. This table only gives areas to the left. And we actually want the area to the right. 0.9599. Okay, so let me pop back. So the table says 0.9599, which is actually over here, 0.9599. What we want is this. Okay. So anybody? I think it's 0.0401. You guys get that?
Yes.
Yeah. Now, so the p-value is actually twice this because it's a two-tailed test. Okay, so this is actually 0.0802. And again, you have to double it because you were saying in a two-tailed test, what's the probability of going in either direction? At least this much. But when you say at least this much, again, either direction that much, which really means what's really happening here is you're saying what's the probability of getting a z-score at least 1.75 or negative 1.75. The probability you're really doing is both of these tails together because you said, well, it could go either way. How probable is that? Well, it's 0.0802 because each of those tails has the same area. So again, just to highlight, I'm just kind of trying to explain this. P-value is 0.0802. Okay, and that's really big, especially given that we said significant is a 1% chance. And this is much more probable than that. So that's not very significant. It's going to happen 8% of the time randomly. Okay. So again, the conclusion is as before. You make your conclusion. If the p-value is less than the level of significance, we reject the null hypothesis in favor of the alternative. Otherwise, we don't reject the null hypothesis, and you can't support the alternative. Okay, so let's just put it down this way. The p-val is 0.0802, which is greater than 0.01. That's our alpha. It's not less. Okay, so if you go back to the last one, I had said, where is it? Right here. When I said less means you reject the null hypothesis and support the alternative. I'm going to negate this. Okay, so on this one, I'm going to say not less means don't reject the null hypothesis. But that doesn't make it true. Please be careful. Don't reject the null hypothesis and don't support the alternative. Okay. H1 had said that the proportion is not 20%. You can't prove it's not. You have no evidence. At least your evidence isn't nearly strong enough. Okay. Which is all to say, again, we got this, if you go back to the very beginning, we got this sample proportion of 22, basically 22%. They're claiming it's 20% here, and you've got 22%. Well, all we're really saying is that's within the margin for error of 20%. Okay, so if you were to do a confidence interval on this 22.4%, the 20% would be inside the interval. Okay, which would say, yeah, it could be 20%. You can't disprove it. Now, it doesn't prove it is 20%. Please be careful. Just because 20% is within the margin of error, you still don't know what the population proportion is, and you will never know until you survey every single college student out there, and nobody's going to do that. Okay, so you still don't know what it is, but we can't say it's not 20%. It could be. Okay, any questions there? Yeah.
Basically, the p-value is the same as alpha, right?
No, the p-value is the probability, and the alpha is the requirement for the probability to be statistically significant. Okay, so alpha is what you're saying is the level of significance. 1% is significant or less. It's just a rule. The p-value is what you actually got. We got 8% chance of getting something that extreme. Okay, that's way too high if you're saying 1% or less is significant. Does that make sense?
Sort of, yeah.
This is our rule for significance. That's why we call it the level of significance. Okay, this is sort of what I'd call the observed significance. You just pick the rule out of thin air. You make rules before you play games, right? Somebody makes the rules up. So you can pick any rule you want, but don't do 20% for significant, because significant events can't be events that happen 20% of the time randomly. Okay, it has to be rare. So we're saying we don't want this to be something that just happens by chance. It has to be something that happened because there's something going on out in the population. Okay, what we're trying to dial the probability that it happens by chance down to a really low number. Okay, so that if it happens, you're going to say, oh, it's so unlikely to happen by chance, it probably isn't chance. Okay, but the observed significance is basically, if the null hypothesis is true, then there was only an 8% chance of this happening, but that's not statistically significant because I'm setting 1% as my rule for significance. You can change that, but not after you start the game. Okay. Yeah, and in different industries have different rules for what is significant. Go ahead.
So alpha and p-value are both probabilities on the distribution curve, but one is the probability that we found, that's the p-value. And alpha is like the probability that's accepted by whatever industry you're working in.
Yeah, exactly. And in my profession, that is education, everything's 5% for significance, everything. Anytime you come up with a probability that's less than 5%, that would be considered statistically significant. So we always do research on different teaching methods and stuff. And different ways of administering education mostly, but so the rule is kind of a standard rule, and you have to demonstrate that you're kind of fulfilling this to be taken seriously, basically. So on ours, we got this z-score that's 1.75 standard errors above the mean. Okay, and the probability of that happening just by chance is an 8% probability. So the question is this significant, or could it have just happened by chance? Well, it could have. This is actually a pretty high probability that this was just a fluke. And so we're thinking, yeah, we got 22%. Is that significantly different from 20%? No, it's probably just a fluke. I mean, there's a good chance that it was just a fluke. Okay, 8% chance. So even if the population proportion is 20%, 8% of the time you'll get a statistic this high randomly, even when the null hypothesis is true. Okay, so it's just not strong enough. It needs to be very unlikely to have happened by chance. How likely? Less than 1% chance. I don't know if I'm helping. I want to help. Let's go to the next one. So I'm going to stop this recording. Okay, so next we're going to look at section 7.3. This one's on hypothesis tests for a population mean. And now this is where the population standard deviation is known. Now remember, when the population standard deviation is known, we end up standardizing our sample mean with a z-score. So this means we're going to use the normal distribution on this one. When we use the sample standard deviation in place of the population standard deviation, that forces us to use a t-distribution. Okay, now let's just go ahead and start this off. So 7.3, in this lesson we study hypothesis tests about a population mean when the population standard deviation is known. This is not very likely. Population standard deviations require data from an entire population. There are sort of theoretical situations where you might know a population standard deviation, but in practice, this is not the case. Let's just look at a quick example here. But just to make sure you understand, the population standard deviation is rarely known. So in the end, we're going to have to use the sample standard deviation, but that'll force a t-distribution on this. Okay, let's go ahead and jump into the example. So it says the mean IQ for the general population is 100 with a population standard deviation of 16. Your professor believes that the mean IQ is higher for college statistics students. He gathers 35 random statistics students and observes a sample. This is a sample mean of 106 for their IQ. We're going to test your professor's claim at 5% significance. Okay, so you can see we're going to be working with a sample mean, and we're going to take the z-score of that sample mean. And back in chapter 6, we learned the conditions for which taking z-scores of sample means will result in a normal distribution. So I'm going to jump back to section 6.4, where we discuss the sampling distribution of sample means. And maybe you remember the activity. Here, what we did was I created a simulation in class of the rolling of a die. As a matter of fact, we rolled 4 dice and we computed the mean of the 4 dice. And because there's 4 dice, you have to divide by 4, and the averages can be 1 or 1.25 or 1.5 and so on. Okay, all the way up to an average of 6. The only way you can get an average of 6 when you roll 4 dice is if all 4 of them are 6s. That actually never happened. We did get an average of 1. The only way to get an average of 1 when you roll 4 dice is if all 4 of them are 1s. This happened 1 time out of 500 trials, so it's really, really unlikely, but obviously it can happen. Regardless, we got these frequencies from 500 rolls and converted them to relative frequencies, which are estimates of our probabilities. And so the different means created a distribution that was sort of very beautifully bell-shaped. If you do enough of them, it comes out really nice. Now, there are sort of rules about when it's bell-shaped, and we'll talk about that just to remind you. But remember, when it comes to distributions, we always are worried about 3 things: the center, the shape, and the spread. I think we have the shape down. Okay, the real rule is you need to have at least 30, well, 30 should be more than 30 in your sample. And that guarantees generally a bell-shaped distribution, as long as your population is not too weird. In this case, just to kind of remind you, the population we were sampling from were rolls of dice, and every roll is equally probable. They all have a 1/6 probability, as long as your die is fair. But when you do averages from like 4 dice, not every outcome is equally likely. In fact, the most probable values are the ones in the middle. Those are the ones that happen more often. And that's why you get these bell-shaped distributions when you work with averages, and that's really common. Okay, so center, shape, and spread. Let's look at this thing we call the central limit theorem for sampling distributions of sample means. The bottom line is we said that sample means from samples of size n are approximately normal in their distribution as long as your sample size is bigger than 30 or the population you're sampling from is normal. So there's 2 ways to pull that off. The mean of all the sample means is the mean of the population you're sampling from, and the standard deviation or standard error of sample means is the population standard deviation that you're sampling from divided by the square root of n. And it assumes we're sampling with replacement, and of course the sampling process is random and that all the trials that you're sampling are independent. Okay, so this is basically the theorem that covers center, shape, and spread. The center is mu, the shape is normal, and the spread is the standard error that they give here. Okay, so we're going to use all of that as we work in Chapter 7 on this hypothesis test we've got here. Now notice we're going to work with the sample mean, and sample means are normally distributed if your sample size is bigger than 30. So you can see very conveniently we've got a sample size of 35. That means we're going to be able to go ahead and run this test. Okay, so it says very first step says to gather the data and the level of significance and check conditions for approximate normality. So you're going to need this X bar, which is the mean from the sample, and it says it's 106 from the sample. So X bar is 106. We'll need a population standard deviation. Well, for IQ scores, I think they scale them so the standard deviation is known. It's a long story, but standard deviation is 16, and that's a population standard deviation. Sigma. Remember, if you don't know sigma, it becomes a t distribution. The sample size was 35 students. Okay, and remember that what we have to check is either, either n has to be bigger than 30 or the population is normal that you're sampling from. Okay. So check that. Here we've got n is 35, which is bigger than 30, so we're okay on this. Any questions? Okay, so this just has different criteria. Now you have hypotheses. The null hypothesis is similar to before. It's probably easier to do the alternative hypothesis first. The only difference here is that you're testing a claim about a mean. Before it was about a proportion. So we said P equals 50% or P equals 20% on the 2 examples. Those are percentages, which are the same as proportions. Okay. This is means, and means are, a population mean is mu. So you can say that mu is less than some number. Mu is greater than some number. or mu is not equal to some number. So that's the main difference so far, is it's a claim about mu, not p. And then the null hypothesis has to say that mu is equal to to that number. Okay, so I'll say the same number as below. Okay, so on this problem, you believe that the IQ is higher for college statistics students, higher than what? 100, okay, which is everybody else. So again, normally I start with the alternative, that mu is higher than 100, and that's for all statistics students. Okay, the null hypothesis, you just change this to an equal. So mu equals 100, has to be the same number. Okay, now you have to remember this also determines the tail for the test. This points to the right. So just as a reminder, this is going to be a right tail test. H1 decides the tail, because H1 is the thing you're trying to prove. Okay, any questions? Now the test statistic, I'll remind you, see, I'm going to do a little tweaking here. First of all, I'm going to paste in something that I'm going to erase. Remember that you're going to take a z-score, or you would take a z-score. No, you do, because we know population standard deviation. So the z-score of a sample mean would be the sample mean minus the mean of sample means over the standard deviation or standard error of sample means. And based on the formulas I put down over on the right, the mean of the sample means is the mean of the population you're sampling from. And the standard error of sample means is the population standard deviation, which we're assuming is known, divided by the square root of the sample size. Okay, so you'll need that. Okay, and just moving things around a little bit. Okay, so I think we can do this computation. So the sample, oh, and maybe the note should be added. We get mu from the null hypothesis. Okay, so the sample mean was 106. We assume the population means 100. That's what it is for everyone else. So that's kind of a status quo assumption. Sigma was 16. And then you divide by the square root of n, which is 35. Now, there are no decimals anywhere in what I wrote down, so I won't be too surprised if evaluating this gives a number that doesn't have a decimal. So it usually gives decimal answers when you ask decimal questions. If there's no decimal, it's going to try and simplify as an exact expression. So just a real quick, let me just show you what I mean by that. Hang on. I'm having trouble. There we go. Focusing, trying to focus. There we go. All right, so it was the 106 for the sample mean minus the assumed population mean of 100. How many standard are the part? Well, I think the standard deviation was 16. Divided by the square root of the sample size, which was, I think, 35. If I hit enter, it does simplify it, but doesn't evaluate it. And so these calculators that do simplification like this, you have to hit the approximate equal key, which is down right above the enter key here. Make sure you just tap the approximate equal if it does that. And so you get a 2 point, I'll say 2.22. Okay. Any questions? Okay. And then you need a critical value to decide if this is statistically significant. This one's a right tail test. Okay, so remember our H1 said that the mean is bigger than 100. So that makes it a right tail test. Okay, and so we'll draw a distribution here. Label it Z. And Z is centered at 0, and our test statistic was 2.22. So we'll mark that off here. Oh, no, I'm sorry, this is the critical value, my bad. So we're trying to do the critical value. And that depends on the level of significance, and I don't know what that is. So let's go back here. The weirdest thing, it says 4% significance. I don't get that. But maybe I'll mark it down here. Alpha was 0.04. So it's sort of a strange number on that. But we're going to go with it. So with 4% significance, we're supposed to look this up on table A2, bottom row. Let me grab that and erase what I did before. Up 4%, and it's a one-tail test. So 0.04 is right here, and then all the way down to the bottom row. And I think it says 1.751 down there. I'm trying to erase this other thing. But it won't, so I don't know what that's all about. That's fine. You should see a 1.751 there. And again, that was a 4% alpha and one tail. I'll draw a little picture of that. So 1.751 standard errors is considered statistically significant. Just as a reminder, we got for our test statistic, we got 2.22 standard errors. So I think, yes, we can call that significant. It does go out into the tail. So I'll put a mark down for this. And because it makes it out past the required number of standard errors, we would consider it significant. I don't know how significant. I need a p-value for that. Okay, any questions about anything yet? This is weird stuff, so please don't feel shy about asking questions. Okay, now the p-value measures how significant it is, sort of on that sliding scale. So there's a picture here again with a right tail test. You have the alternative hypothesis saying mu is greater than something. Left-out test has H1 saying mu less than a value. And of course, the two-tailed test, H1 says mu is not equal to a value. Okay. So I think we're doing a right-tailed test because we're saying mu is bigger than 100. So let me go ahead and draw a right-tailed distribution. And on this one, you label the test statistic, which is the 2.22 z-score. So that's the area you want to find. Okay, any questions about that? Table A1 has areas under the normal distribution. So you just find your z-score, which is 2.22. This way. Let me pop over to that real quick. Table A1. And so hopefully you're seeing what I see here, which is 0.9868. Okay, any questions? That's not the p-value. This is giving the area to the left always. Don't forget, only gives areas to the left. This is a right-tailed test, so we need to doctor that a little bit. Okay, so 9868 is what it says. That's the area to the left. We need the area to the right, so we have to do 1 minus 0.9868. Can we do that yet? Oh, 0132, thank you. 0.0132. That's our p-value. And I'm just going to move things around a bit so to kind of get rid of some of this clutter. Or at least to make it a little more clear, I feel like I need to draw a line to separate the diagram and what I drew for that. All right, so that's a small p-value, it's less than 5%. I don't remember what the alpha value was, so I'm going back up. Yeah, it was 4%, okay, 0.04 for alpha. And that's the critical part. So the p-value, 0.0132 is less than 0.04, which is alpha. Now this is, again, I have this sentence written again and again throughout all these documents. Make a conclusion if the p-value is less than the level of significance, yada, 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 we reject the null hypothesis in favor of the alternative. Otherwise, we fail to reject the null hypothesis and don't support the alternative. So that's a wordy, sort of a wordy way to conclude, but maybe I would be willing to copy this down that we wrote on the last lesson. So, because it's always this idea. Small p-value causes rejection of the null hypothesis. So I'll paste that in, and that will be the rule for the rest of the semester. And it's just a kind of a brief way of explaining what I explained in this paragraph here. Okay, so p-value is less than or equal to alpha, so we reject the null hypothesis. Null hypothesis says that the mean is 100. We're not going with that. But we are supporting the alternative, H1, which said that the mean is greater than 100. I don't know what, I'm not saying what it is. I do have 106 from a sample, but that was only like 35 students. And there's a lot more statistics students out there. So it's silly to act like you know what the mean is. But we have evidence that it's more than 100. And so we can speak with a certain amount of confidence on that. So we'll say the data are what tell us this. They support the claim that the mean IQ for stat students is greater than 100. Okay. Easy. Just going to pause and wait for questions. Okay, no questions. So we're going to go to the next one. It's just another example, basically the same thing. It says from 75 random patients, a 200 milligram tablet of acetaminophen is given, and the body temperature is measured after 2 hours. Their mean temperature is 97.8. Assuming the population standard deviation is 3.5 degrees Fahrenheit, tested claim at 3% significance that the mean temperature is below 98.6 degrees Fahrenheit 2 hours after taking acetaminophen. And that's just Tylenol. We know Tylenol is pretty good at lowering body temperature. Okay, it's one of the good ones. So let's see how this goes. So sample data, we're basically a sample size of 75. We got a 200 milligram tablet of acetaminophen. Again, that's Tylenol. Body temperature is measured after 2 hours. The mean, here we go, this is from a sample. So the mean temperature is 97.8. Assuming a population standard deviation, okay, that's sigma for population standard deviation, is 3.5. Tested claim at 3% significance, that's our alpha, 0.03. That the mean temperature is below 98.6. That's an alternative hypothesis, mean below 98.6. People have used to assume that the average body temperature is 98.6. I think it's a little less than that. I think I've read that the mean body temperature has gone down over time too, just a little bit, just a tiny amount. I can't remember why they were saying that. Okay, but regardless, they're saying the mean is less than 98.6. So let's take our alternative hypothesis and say the mean, which is mu, is less than what they're saying here, 98.6. Okay. So generally, again, I always do the alternative first, because that's usually what they claim, and then you go in and say, all right, well, they're saying it's greater, but for the null hypothesis, we have to assume it's equal. That's what we're comparing to. And we use it for our z-score that we compute next. Oh, I didn't do my check. Where's my check? What should I write for my check on this one? Anybody remember? N has to be how big? Daggone it. Good try. Then now the 10, yeah, the 10 is for proportions. So we're doing means, and means have different rules. So here, mean, when you do means, the sample size needs to be bigger than 30. So sorry, sort of a trick question. Okay, so I hope I wrote that before. Let me double check. Check either n is bigger than 30 or the population's normal. We're good to go. Okay, test statistic. This is Z test statistic. Z is x bar minus mu over the population standard deviation, which we're assuming is known, divided by the square root of the sample size. So x bar was 97.8. The mean is assumed to be 98.6. That's what people have always said. And then over sigma, 3.5 divided by the square root of n, which is 75. So see if you can get what I get. Be negative this time. It's a left-tailed test. Type it in when you get it. 2 places after the decimal. Yeah, thank you. Negative 1.98. So that's almost 2 standard deviations below. Seems significant, but I'm not ready to decide that until I get my critical value. So on the bottom row of table A2, remember that's the one that asks for degrees of freedom. That's for t-tests. Z distributions are just under large here, and in parentheses we write Z. Okay. Our alpha was 0.03, I think. Yeah. 0.03, and this is again a one-tail test. I should have denoted this. On H1, mu is pointing left. Okay, so that makes it a left-tail test. Which main thing is it's not a two-tail test. So we'll just write one tail as opposed to two tail. Make sure you look up under one tail. Okay. And I'll pull this up real quick. It's again table A2 for the critical values. And one tail 0.03, is it here? Yeah, it is, right in the middle there. There's a 0.03 for one tail, and then all the way down. Make sure you got that. One tail, 0.03, looks like 1.88. That's the number of standard errors for statistical significance. Any questions? Okay, so it says 1.881 standard errors. Now remember, this is a left tail test, so what that means is standard errors below the assumed mean, which makes this a negative z-score. Negative 1.881, because it's just a left tail test. You just have to make this negative. I get it. Okay, so, and then don't forget our z-score, the test statistic, is coming out to the left of this. So the negative 1.881 is a critical value, but the test statistic was negative 1.98. And because that's in the tail, we consider that significant. Statistically significant. Okay, any questions about that part? Okay. Then comes the p-value, table A1 still. So, or table A1, I should say. So here we go. This is our test statistic now. Find how probable it is to get something this small. We got negative 1.98. So we have to go down, for z, we go down to negative 1.9. And then over to 0.08 to get that probability. Remember, this table gives areas to the left of your z-score. That's what we want, actually, because this is a left tail test. Okay. So, the area to the tail to the left is what gives the p-value. Okay, so let me jump over to table A1. This is a negative z-score, so here's negative 1.98. This is what I see, 0.0239. Any questions about that? This again is a left tail test. This table gives areas to the left, so that's a good number right there. That's our p-value. Okay, any questions? All right, so 0.0239. That's our p-value. Any questions? Okay, and then you can make your conclusion. Same as before. So our p-val is 0.0239. I'd consider that statistically significant, and it's less than 0.03, which is our alpha level of significance given the first step. And I wonder if I still can paste that last thing I did. Yep. So those are the criteria for making a decision. Okay, if p-value is less than alpha, you reject the null hypothesis, support the alternative. So here we're rejecting the claim that the mean body temperature is 98.6 when you're on Tylenol. In fact, we're going to support the claim, the alternative, that the mean is less than 98.6. So the body temperature is now brought lower when you put someone on Tylenol. And the data are in support of that. So I'm going to somehow squeeze all that in. There it goes. The data support the claim. That the mean body temperature is less than 98.6 degrees Fahrenheit 2 hours after taking Tylenol, I think, which is called oh Lord, what's it called? Acetaminophen. Acetaminophen. Yeesh. There you go. Okay, any questions? So it's the same. The next two problems are the same as well. But we go with sigma unknown. And we talked about this. I'll mention again in a second. Just waiting for any questions at all. Okay, so we're going to start on section 7.4 here. This is more hypothesis testing for a population mean, which is what we did in 7.3. But now we're assuming the population standard deviation is unknown. And as you know, when you don't know the population standard deviation, you have to substitute in the sample standard deviation. And when you standardize your mean, using a sample standard deviation creates more variability because every time you do it, you get a different standard deviation. And more variability in the standardized statistic, which is going to be called T, just means it's not going to follow a normal distribution. So this is going to be what people refer to as a t-test. And it's the first one. They get more complicated later, but this is the first of our t-tests. Okay, so let's just jump on in. Says in this lesson, we study hypothesis tests about a population mean mu when the population standard deviation sigma is unknown. So let's go ahead and read this. It says the mean roll on a fair six-sided die is 3.5. That is true. You think your favorite casino is using loaded dice. So you very cleverly steal one, forgetting there are video cameras everywhere. At home, you roll the die 1,000 times, and the mean roll is 3.35, which seems a little low, but I don't know if it's significantly low. It could just be a random thing, with a sample standard deviation of 1.78. Test the claim that the die is not fair at a 1% level of significance. Okay, now again, you notice that sample standard deviation here. Are there any questions? Okay, so here it's a claim about a population mean. So when we set up our null hypothesis, it'll be regarding mu, all right? But anyways, as we gather our sample data, it's pretty obvious. We're gonna just write down what they gave us here. The sample mean is the 3.35 up above. It's not the 3.5, that's the population mean, which will come later. And and by the way, it's a hypothetical mean. They give a sample standard deviation of 1.78. And the sample size looks like is 1,000. You're that bored. You roll the die 1,000 times. Any questions? The check is that n needs to be greater than 30, or the population should be normal. So here, n is 1,000. Clearly that's bigger than 30, so we're good to go. Okay, we know that sample means have bell-shaped distributions as long as your sample size is big enough. Any questions? All right. Then our null and alternative hypotheses. So the null hypothesis is always mu just equals some value. Okay. The alternative has three possible forms as usual. You can say that mu is less than the value. Mu is greater than the value. Or mu is not equal to that value. Okay, and these determine the type of test. Less than means left tail test. Greater than, obviously, is the right tail test. And then finally, the not equals are two-tailed tests. Okay, any questions? So for our problem, it's saying, let's read it real carefully here. You think your favorite casino is using loaded dice. Now, so that means you don't know whether the mean is bigger than 3.5 or less than 3.5. Remember, the mean should be 3.5 on a fair die. Okay, but you don't know. So
I have a question there about that supposition. So, I mean, in sort of a real world scenario, I guess if we were trying to actually determine if a casino was cheating us on dice, wouldn't we assume they were they had biased dice in their favor? So like depending on the rules of the game, we could assume that the dice were either, biased one way or the other, greater than or less than.
Wait a minute. I don't know what you mean. So
well, like
why would we assume that they have, but why would we assume they have biased dice?
It's a casino, and we think the dice aren't fair.
Well, it's illegal. I mean,
I guess my question is not about, I'm not so much trying to derail the question here. But I guess what I'm trying to get at is, like, if we had a reason to assume that the dice were one way or the other, then the appropriate test would be a left tail or right tail test. Is that the case?
No, I think I mean, to be honest with you, the way the problem is posed is that you've decided to verify that the die, you want to try to prove that the die is loaded. So initially you don't have a sense about whether it would come out larger or smaller than 3.5. Does that make sense? If you just think it's loaded, then you would expect the mean to be different from 3.5.
Yeah.
So I would say before, you have to be careful because these are supposed to be set up before you've gathered your data. If you think about a scientific process, it's always hypothesis and then gathering data.
Right.
So we're creating hypotheses. The idea, it's a really weird reason why we ask that people to try to formulate their opinions before they get the data. And that's just because we try to avoid this thing that's called data mining. And data mining is where you just have data, lots and lots of data. And you look for weird quirks in the data, and you don't really care what you're looking for. You're
Right.
just looking for anything that stands out. And I think the idea is that if you look at data long enough, you'll always find quirks. And that's not necessarily because there's anything important happening. It's just eventually something random is going to pop up.
I think I'm
And-
gonna get that. I think I'm gonna have those. I think I'm gonna have those quirks in my project data for this class.
Okay. Well, the point is that you don't want to formulate your hypotheses or your scientific theories based on you just randomly scouring through data and hoping to find something that'll impress people. Because that's not based in some theory or logic, because there's nothing that sort of prompts it. There's no reason to think that you wouldn't eventually find something random that would be sort of interesting. But that doesn't mean it's supported by any hypothetical theory. So that's why we like you to make the rules of the game first. You have something you're working on. We want you to tell us what you think might be true, and not just go looking for things that you've not thought about, that there's no theory to support. So that's why we want to make the rules of the game first, so you don't become one of these data miners that likes to publish stuff just to get attention. You know what I'm saying? So that's not thoughtful scientific process. So that's the best I can say for why technically we want to put these theories out, for the hypotheses first, before we go out and start making decisions based on data that are going to do random things. So having said all of that, we think the die is loaded. We don't know what the average is going to come out to be. It could be above what it should be or below, but we would think one of those would happen if the dice are not fair. So that's why you're probably going to go with a two-tailed test on this one.
Great. Thanks.
Sorry?
I said thank you.
Okay, so the null hypothesis would just say, yes, the die is fair. So the mean comes out exactly at 3.5. Okay, where the alternative, which you're suspecting is the case, is that it's not 3.5. Okay, don't know if it's less or greater. I just think it's a bad die. Okay, because I don't trust these people. Okay, any questions? Okay, so then we can do our test statistic. This is just going to measure how many standard errors the sample mean is from the population mean. So the test stat, we in most of the graphics I abbreviate TS. So this is a T statistic because you're using a sample standard deviation, which varies more than a Z statistic, which doesn't have a sample standard deviation and doesn't vary. So the only thing, this one has two variables, the mean and the sample standard deviation, changing every time you gather a sample. All right, so our X bar is 3.35. The mean is supposed to be 3.5. Standard deviation is 1.78. And square root of n is 1,000. Okay, y'all. So if you guys would just please compute this, and when you get it, just unmute yourself, and anybody, if you'd let me know what you get, that would be awesome.
Negative 2.66.
Yeah, that's good. And I think 2 places after the decimal will be fine. Negative 2.66 is great. Now, the question, now this looks significant, right? Because now you're approaching 3 standard errors. So I can't imagine this won't be statistically significant, but we'll still go through the process here. Let's get our table A2. So the degrees of freedom, now this is going to be a little pitiful. Remember, degrees of freedom on a T statistic is n minus 1. So on this one, n is 1,000. So you have 999 degrees of freedom on this. So that's going to go into the large category. I don't know if you remember that bottom row, just eventually gives up and it says large. So that's where we're going to be. What's our alpha? 1%. Okay. So our alpha is 0.01. This is a right tail, left tail, or a two tail test, you guys?
Two.
Yeah, it's a two tail test. Not equal means less or greater. So then we're going to do two tails for our alpha. All that does is it splits it among the two tails instead of just putting it all in one tail. Okay, like that. And let me see if I can bring that thing up. Nope, not going to be so lucky. So I might have it at the end of this lesson. Let's see. Ooh, I do. Okay, so I'm going to pop back over to that table. Now, this is where you begin to really see the limitations of using tables. Here we agreed is 0.01 two tails. So this is actually the first column of the table here. Okay, 0.01 two tails. If you go all the way to the bottom, way down, you'll see you just end up, oh, hey, wait a minute. There is a 1,000 degrees of freedom, and that's the closest you're going to get. So I think we'll use the 2.581 rather than the 2.576. Of course, those are almost exactly the same. Okay. Now, again, you can see how the degrees of freedom sort of jumps. Once you get up to 50, the next one's 75, next one's 100. And so I would say just use whatever's closest. You know, if you're at 10,000 degrees of freedom, you're effectively at the Z distribution. So, you know, 1,000, you know, you can use the, you know, anything close to 1,000, but after that, just go to the Z-scores. Okay, any questions? Okay, so let me go back here. So I'm gonna leave it at 9. Oh, I forgot. Did it say 2.581? I think it did. So I'm just gonna make a note here. We actually used 1,000. Because that was the closest one here, but that's just in case you go back and look at this and wonder what the heck that number came from. Okay, but it's supposed to be 999. Okay, so this is called the critical value. If you were to draw this, you have to remember it's a two-tailed test. On the T distribution with two tails, then there's really two critical values. So there's a negative 2.581 and a positive. And so if you go past that, in either direction, you have statistical significance. Is there any question about that? So just to kind of add that, maybe we'd say something like that the negative 2.66 lands in the left tail, so it's statistically significant. So the test statistic lands in the left tail. it's is statistically significant. It's harder to be statistically significant when you have an alpha of 0.01. These critical values are actually pretty extreme. You're requiring 2.581 standard errors for statistical significance. We did get that, but that's a pretty high bar. You know, when you think about, we always used to say 2 standard errors was unusual. Okay. Any questions here? That's the critical value. Let me show you the p-value next. This one says to use table A3, which is a new table. So it's, it's a beautiful creation of mine that is terrifying, actually. So for what we do on table A3, let me go ahead and draw this first. So couple of things. Our test statistic is what you plot for this. And again, that was the negative 2.66. There. And the p-value is the probability of getting something at least this extreme, but it could happen in either direction. That's the main thing you have to remember. What's the probability of getting something this extreme in either direction? Well, you have to double this. So I think, you know, kind of what's happening here is I'm also counting the right tail that starts at the negative 2.66. I'm not going to write that down just because it kind of muddies this, but still t distribution. And how do we get that tail? We have to remember that the table we've been using for p-values has been the normal distribution. That's not it, right? This one. The last p-value we just did today was from the normal distribution, but I've spent all this time arguing we're not using the normal distribution anymore. So if you go through this list, critical values are not probability values. Remember, p-value stands for probability values. So that a critical value is not a probability. And you just look at these numbers, probabilities are always between 0 and 1, and none of these are probability values. So let's go down. So the very last couple pages of the handout are sort of terrifying. But for a math teacher, super cool. And what I wanted to do is just sort of highlight, and we're gonna have to do some rounding here, but I think our test statistic was negative 2.66. Does that sound right to you guys? And we have 1,000 degrees of freedom. So what I'm gonna do is I'm gonna find 2.7 on this. So first of all, my test statistic, notice these are rounded to the nearest 10th here. Was it negative 2.66 though? It was, right?
Yes.
And yeah, and instead of the top row being for the hundredths place, these are degrees of freedom. So the bottom line is this table is a little less precise because your t statistics don't go out to the nearest hundredth, they only go to the nearest 10th. Okay, so you'll use this top for degrees of freedom. There's no way around it. I believe again that our t statistic was negative 2.66, which we're going to round to negative 2.7 here. And then for degrees of freedom, I don't know if you can see it, but there's a 100 out there, and then there's infinity. Okay, those are, once you hit infinity, you're using the z distribution. Just letting you know. Okay, because the t distribution approaches the normal z distribution. But just to practice using the table, again, we're going to round our t statistic to negative 2.7, and then we're going to go all the way out to infinity degrees of freedom. Okay, so I'm going to try and do this here. 2.7 all the way down 0.0035 is what I see there. Okay, any questions there? I'll copy, that's going to be basically our p-value, roughly 0.0035. You'll see that we have a better way of doing it. I did not mean to close that. Let me go back. Okay, so 0.0035. All right, so what we did was for table A3, our T statistic, you've got to go down to negative 2.7. Okay, that's our test stat. Rounded a little. Okay. And then degrees of freedom. Let me do it this way. Okay, technically, what you really want is to go out to 999 degrees of freedom, but you can't. So I'm going to go ahead and say out to 999, and then in parentheses, I'll say we used infinity. Okay, it just gets up real high, and eventually you're using the normal distribution. And the idea is it's just indistinguishable from the normal distribution at that point. So you may as well use the normal. So negative 2.7 and 999. I don't remember what it said. Was it 0301, anybody?
That was 3.5.
035?
0035.
Aha, you're the best, thank you. So it said 0.0035. So that's sort of the area of the tail here. But do remember, you have to double this on the two-tailed test.
Oh, yeah.
Okay, so for our p-value, you're going to do 2 times 0.0035. So we'll just say 0.007. 007. Get it? James Bond? Told you statistics was cool. Okay, any questions? All right, so real quick, I want to jump over to Canvas with you. And just show you what I've got here for you. Okay, so under modules, I don't know if these are published or not, and I'll make sure they are. Okay, p-value calculators, boom, it's published. So if you go into Canvas, modules, there's a module called important bits. The p-value calculators will allow you to not have to do any p-values from tables. So we're doing students T distribution, and this is much more exact as well. So we're doing students T distribution. So you just click on that. And then all you have to do is dial in your degrees of freedom. So this won't be an approximate value. This will be much more, well, I mean, everything's approximate, but it'll be much, much, much more precise. I think our z-score was negative 2.66. Okay, so there's our area of the tail. It's actually 0.00397. Okay, and you would double that. It's kind of cool the way you can, I don't know if you noticed, there's a slider for degrees of freedom. And you can see how when the the degrees of freedom are small, the T statistic varies, or the T distribution really varies a lot. And you see how big the p-values would be with 1 degree of freedom. And this is a really strange looking distribution. But you go up to, to hit 30 degrees of freedom, and after about 30, the distribution kind of stops changing because you're effectively doing a normal curve at that point. So going back to 999, there it is, 0.00397. We had gotten 0035, which is close. Okay, but you'll have this available to you at the exams. I think you find this is much easier to use than the table. Okay, and feel free to have fun with that. If you're curious about how these computations are made, they're inside this folder. It's actually pretty ugly. Part of this is just me drawing the curve, but that's all buried in there. Okay, let me go back to the handout. I think we have another example to do. Any questions about that page that I was just showing you? Okay. All right, so here we are again. Only thing that's left is to make a conclusion. One way or another, you've got this p-value, and it's going to be close to 0.007 one way or another when you double it. And so our p-val is 0.007. I think our alpha was 0.01 right here. So it is less than alpha. And it says if the p-value is less than the level of significance, we reject the null hypothesis in favor of the alternative. So that means we're going to reject HO. We're going to support HA, and that would say that the mean roll on the die is not 3.5. So what we had was pretty significant, and that means we're probably being cheated by the casino. So the data support the claim. That the die is not fair. Which means the mean roll is not 3.5. You have to remember, you wouldn't have gotten 3.5 on a sample mean. Okay, just because it doesn't come out at 3.5 doesn't mean the die is not fair. It's not going to be exactly 3.5. It's going to be different. So the question is, how different is it? Before you start saying the die is not fair, you need to show that it's significantly different. And that means it's a very low probability to get what you got if the die is fair. If our die was fair, the mean we got has less than a 1% chance of happening, okay, based on our p-value, if the die is fair. That's a very unlikely outcome. It happened, so I don't think the die is fair. Okay, any questions? So that's one. There's another one here to do. So let's go to this. This one is based on some nonsense, actually. I made up almost all of this, but it was based on something my dad used to say. We lived in a house, or I should say, he owned a house that had glass in the windows that had drip marks, and my dad, where the glass was just sort of running, and my dad used to say, "Yeah, old windows run." And that the glass is actually a liquid that just moves really slowly. And I looked into it once because I thought about it years later, and I don't think it's true. People say that glass is what they call an amorphous solid, but I don't. Based on everything I've read, it doesn't run. Even if it's hundreds of years old, I don't think glass runs, but people still say it does. I've heard it said in multiple scenarios.
I've heard that too.
Yeah, yeah, but I don't know. I mean, if you just read about it on the internet, like someone that knows what they're talking about, maybe I don't know where you find them, but anyway, a cathedral in Europe is over 500 years old, with hundreds of panes of glass in this cathedral. The panes were originally manufactured to be a quarter of an inch thick, but now the bottoms of the panes appear to be slightly thicker. Oh yeah, the glass is running. A random sample of 125 windows were measured at the bottom, and the mean width was 0.256. Well, that's not much thicker. Is it significant? I don't know. With a sample standard deviation of 0.031 inches. Test the claim at 1% significance that the mean thickness at the bottom of the windows is greater than 0.25. Okay. So simple enough. Let's even find that sample mean. That's the 0.256. Does anybody see a standard deviation?
Was it 0.031?
Yeah, is that the standard population or sample standard deviation?
That's the sample.
And if it's a sample standard deviation, is it the Z distribution or the T distribution?
The T?
Good. You win. You win the prize. So you've checked 125 windows. Okay. Let's get that level of significance. Alpha this time is 1% again. So our alpha is 0.01. Pretty strict. I think we just need to check our conditions. So the N is bigger than 30, so we're okay to go again. For normality, the sample means will follow a normal distribution. So the probabilities you get will, this is a little more complicated. When you standardize your sample mean with a sample standard deviation, then the probabilities will follow a T distribution. Okay, null hypothesis and alternative. Okay, so does somebody feel brave that would be willing to say what the alternative hypothesis is? I'll start you off. Mu, the mean, and then what do I write? Less than, greater than, or not equal to what?
Is it not equal to P?
Now there's a number that you want to put. So if you look at how we did the last one, it's going to be just like this. These are your choices. Okay, so you can say the mean is equal to a value in the null hypothesis, but the alternative has to say mu is less than, greater than, or not equal to a number, an actual value. So that when we did it for the die, we said that the mean was not equal to 3.5. Okay, so this is a different problem though. So, it's not going to be 3.5, and it's not necessarily going to be a not equal. So look at the claim in the very last line, and then just tell me what to write. Anybody?
Greater than 0.25.
Yep. So we're going to say the mean is greater than 0.25, and the null hypothesis, the mean is just equal to 0.25. Is there any question about that? Just got to read it carefully. It's going to be there somewhere in the problem. Okay. It says, and the word is the mean. So mean is mu. Okay, so then the test statistic, because we're using a sample standard deviation, this is a t-test. So t is x bar minus mu over the standard error, which is s divided by the square root of n. So x bar is 0.256 minus mu, which we're assuming is 0.25. So that's a small difference between these two. How many standard errors? Don't know. 0.031 over the square root of n, which is 125. Okay, y'all, so take a second and do that and let me know when you get something.
0.004.
That was so fast. Did you say 0.004?
I did.
It seems too small.
Well, I'm notoriously bad at calculations.
So 2.16.
Yeah, that's what I got too. Sorry, Dan, 2.16.
What did I do? Oh, yeah, I see what I did.
Good. I was gonna say, should we debug it?
No, I just wasn't paying attention when I typed the formula.
Oh, good. Okay, so so that's actually 2 standard errors bigger than it should have been. These windows were
Okay.
manufactured to be 0.25 inches thick. They're a little thicker. It doesn't seem very much thicker, but it's actually 2 standard errors thicker. So normally that's statistically significant. And yet, with a tiny level of significance, it's harder to prove statistical significance. So let's see how many standard errors are required here. So when you go to table A2, I think there's a 100 degree of freedom in here. So for degree of freedom, technically the degrees of freedom, remember, are n minus 1. There's 125 windows. So 124 degrees of freedom. Okay. The table's not going to have 124 degrees of freedom. We'll probably use 100. I'm just going to put a 124 down there so it looks right in the notes. But in reality, we're going down to 100 degrees of freedom here. Okay, and again, our alpha is a 0.01, but it's a one-tailed test this time, I think. So you have to look at one tail 0.01 here. Okay, and then bring those together. So let's see if I can draw this in here. Right there, I think. I'll zoom in on that. So that's what statistical significance means in this problem, 2.364 standard errors. Any questions? And we didn't get that. 2.364 is statistical significance. Any questions? Okay, so let's go back to that.
So why did we use the one tail this time?
Yes, because this is a right. Remember think of the alternative hypothesis as pointing to the tail. So this one has mu greater than. This is pointing to the right. So this is going to be a right tail test. The only time you do two tail is when it's not equal. Is that clear?
Yeah, thank you.
Good. Right tail is one tail. I forgot what it was. Does anybody remember what it was?
Was it 2.3?
2.364.
2.364?
Yeah.
Thank you so much. So it's 0.01, one tail. Okay, 2.364. You can draw that if you like. But the point is, we didn't get 2.364 standard errors.
I realize that the real answer to this is probably like just to frame the question for the classroom environment, but why did we choose such a restrictive alpha for this test? Like how, or more generally, how do we choose alpha?
Okay, well, look, first of all, you understand I just made this thing up out of thin air, right?
I do,
So
yes.
this is not real. And second of all, because I hate to say it, do you really want to know? I hate to say it. I'm
Well,
everything.
if you, I don't want to make you hate something, so you might as well.
No, everything here, first of all, is in bad faith. If I make something up, you can't trust any of it. Okay. There's no goodness in any of this. So I didn't want this test to pass because
Because you wanted to prove your dad wrong.
because all the scientists say that glass doesn't run. So I picked my alpha so the test would not pass. Are you happy?
Yeah, I think I knew that already. I think
I'm a
more
fraud.
generally, it's okay. It's for our benefit. More generally, like, I guess, do we always just take the alpha of like our respective fields, or do we ever tweak alpha based on?
You've asked, so give me a few minutes and I'm going to address that.
Okay, great.
Let's finish this problem. Here we go. This is our alpha of 0.01. This 2.16 standard errors is not significant. I'll just abbreviate. Okay, so that is what we're getting from this critical value. And then the p-value is sort of the more important number. So let's do this real quick. So we're going to table A3. The t statistic now, here we have, again, 2.16, which we're going to round to 2.2. So this is me rounding the test stat. I'll just write TS to 2.2 right there. Okay, and then for degrees of freedom, again, you would normally go out to 124 if the table had it. It won't. So I think we're stuck with 100 on this one. But I still put the 124 up here just to show you what you would be doing. If it's not there, you just pick the closest one. Just remember that, okay? And when it starts skipping like this, it's skipping because the numbers don't change that much. Let me flip back over to that table real quick. So it's 124 and 2.2. So 2.2, I'll go ahead and circle these first. 2.2, and then we're going to go all the way out to 100 degrees of freedom here, which I think I don't have room for. Here we go, 100 degrees of freedom. Second to last. Okay, so there it is. I'm going to zoom in. It says 0.9849. And you have to remember these tables give areas to they're called cumulative distributions. And what it is it's the area accumulates to a certain point that you're looking at. So this is the cumulative area of everything up to the t statistic that we looked up. So that is another way of saying that this is the area to the left. Up here, you can see it says the area to the left of the test statistic is given. Okay, so it's cumulative 0.9849. Let me go back to the notes somewhere and put that in. Okay. All right, so remember, this is a right tail test, so you don't want the area to the left, you want the area to the right. So our test statistic is 2.16. This is the p-val. It's a right tail test. We have to use the complement of the area to the left, 0.9849. The p-value will be 1 minus 0.9849. Okay, so that's 0.0151. So it's just a little bigger than 1%. 0.0151. Okay, so when it's bigger, then you fail to reject the null hypothesis. And notice it says, again, if the p-value is less than the level of significance, you reject the null hypothesis. Otherwise, we fail to reject the null hypothesis, never support it, which means you can't support the alternative. So p-value is 0.0151. This is greater than 0.01, and that's our alpha. Okay. We would fail to reject the null hypothesis. Which means we don't support its alternative. Remember, those are opposing claims. So you have to reject one to support the other. So we don't support the alternative hypothesis, which had said that the mean thickness is greater than 0.25 inches. So the data do not support the claim on this level of significance. That the mean thickness of the glass, let's just say the windows at the bottom, is greater than 0.25 inches. Okay. Any questions? I guess I'll show you that p-value sheet again. I'll let you catch up. So I'm going to pop over real quick. And again, this one, the degrees of freedom are 124. And what's the test statistic? It's 2.16. So I'm going to pop back over to that Desmos page that has the p-values for the t-distribution. So now you're looking at it. Again, degrees of freedom is 124. I'll just put that in. Okay, the test statistic is positive this time. It'll naturally just switch over to give you the right tail. The way I wrote this one was it would give you the area of the right tail when the test statistic is positive. So this one's 2.16. So our more accurate p-value you can see is 0.016 here. Right here. That's this notation is a tail, the area of the tail. I didn't put p-value there because sometimes you have to double it before it's a p-value. If it's a two-tailed test, you end up doubling this. So in general, it's just the area of the tail, which may or may not be a p-value. Okay, so in this case, it's 0.016. We had written 0.0151, which is pretty close. And good enough for government work, I suppose. All right, now, before we take leave of this section, I'm going to go ahead and do what I said and talk about alpha. So let me switch back over to my iPad. I should have done this before, but it's just one thing always pushes out another and it's hard to squeeze everything in. Okay, hang on. Okay. This is a topic that goes actually in 7.1, which we skipped. So we'll just put this under choosing alpha. Okay. That does not look like an alpha. Let me fix it. First, you have to know about errors. Okay. Alpha is chosen to minimize a certain type of error. Okay. So there are basically two types of errors. We can make in a hypothesis test. And we're not talking about arithmetic mistakes. You know that sometimes people take the COVID test and they get a false positive, which means they're told they have it, but they actually don't. That's an error. It's nobody's fault. It's just the way they set the test up. If you go over a certain mark on whatever they're measuring, they call that a positive. And sometimes it's not. I mean, they're looking for antibodies or something like that. So there's something rises to a certain level, it crosses the line, and boom, you're positive. Most of the people that cross that line will be positive, but some of them will be false positives. Then there will be other people that are sick where that reading doesn't cross the line. Okay. They're sick, they should be called positive, but because their reading doesn't cross the line, they're going to be classified as a negative, and that's a false negative. So again, you have false positives, you have false negatives. It's just a question of whether the line, whether your reading crosses the line or not. And our line in a hypothesis test is a critical value. If the test statistic crosses the critical value, you're going to reject the null hypothesis. Okay, sometimes that'll be a bad decision, not because you made a mistake, but just because the test statistic was misleading. Okay, so sometimes you won't cross the line when you should have, and you'll be making the other mistake. So let me go ahead and define the the errors here. A type 1 error this is rejecting the null hypothesis when it's true. Okay, the type 2 error is the other, obviously. So it's like false positive, false negative, but it's not a medical test, so we use different language. So here, a type 2 error is failing to reject the null hypothesis when it's false, which is a mistake. Okay, now, very simply, if we assume HO is true, okay, that was supposed to be a straight line. Okay, assume the null hypothesis is true. You're doing a hypothesis test. You've got a critical value, CV, okay? The area of the tail is alpha, okay? The probability of getting a test statistic that's bigger than the critical value is alpha. I'll just go ahead and put a little test statistic right here. Yeah. So the probability of a test statistic being greater than the critical value is alpha, and you can just see that from the diagram. Alpha is the area of the tail. You're going to reject the null hypothesis if the test statistic ends up bigger than the critical value, because the p-value will come out smaller than alpha. Okay, as you can see, the p-value goes past the test statistic. So the probability of getting a test statistic being greater than the critical value is alpha. When this happens, you'll reject the null hypothesis. I'll say you'll reject the true. Remember, we assumed it's true. Null hypothesis. Okay. And have committed a type 1 error.
Okay, so we're trying to like set an alpha that will be at least as extreme as the unknown population parameter, but we don't know what that parameter is.
I think you can make it easier than that. I think you can just say, when the null hypothesis is true, alpha is the probability of a type 1 error. And if a type 1 error is a really bad thing, you should pick a small value of alpha. Okay. So just a little, so we could say that assuming the null hypothesis is true, alpha is the probability of a type 1 error. Let me make a little space for that. There's a given that, and it's a conditional probability given that the null hypothesis is true, but I've got that up above. Okay. Now, beta is the probability of a type 2 error. It's a much more complicated number. Beta, that's the Greek letter, is the probability of a type 2 error. And I'm not going to go into a lot of detail on this because I just don't have time. Okay, what we know is that smaller alpha forces a larger beta. It's sort of like if they'd written the medical tests to minimize the number of false negatives, what they're doing is they're lowering the critical value so that fewer people will cross it. Sorry, this would eliminate the, false negatives are if you're on the left side of the critical value when you should be on the right, so you lower the critical value. But if you're going to lower the critical value, you're going to end up with a bunch more people crossing the line that shouldn't. And maybe I should draw you a little picture. Okay, there's a number line when you do a medical test. And you think about the population of people that are out there that are positive. Most of them have some reading that's just high. And normally these are normal in distribution. Normally they're normal. Okay. So these are positives here. All these people that are actually sick. Okay. Now the negatives should come out lower on whatever reading they're taking. I have no idea, but most of the negatives are going to come out lower. Okay, so there's really two populations here. And so the question is, you're the you're the researcher who's designing this test. And where are you going to draw a line? And it has to work for as many people as possible. So where are you going to draw the line to decide who's sick and who's not sick? Well, let's see. I could put the line here. That's my critical value. If you cross the line, you're positive. You're going to be classified as having, COVID-19. Okay, and right now, I've got two false positives. Those two negatives that I'll circle right now, that person and this person, because they've crossed the line, they're going to be told they're sick, but they're not. Okay, now the other thing is there's two people over here that are false negatives. They've been told they're not sick, but they are. So you have to look at these two mistakes, false positive, false negative. Here we have type 1 error and type 2 error. Which is worse? Okay, I think a false positive is worse. Let's see, a false negative is worse than a false positive. Okay, if a false negative, that's because you think you're not sick, but you are, and now you're meeting with people and you're spreading COVID-19, right? So we have to make this judgment. False negatives worse. I need to move the critical value this way. Okay, what's the trade-off? So I had my critical value here. I had two false negatives. Okay, if I move the critical value, now I only have one false negative. But what's the bad news?
You're
Yeah,
getting
you mean on, yeah,
I got more false positives. You follow me here?
yeah.
So reducing the probability of one mistake, that's like having a smaller alpha. Reducing the probability of one mistake forces the probability of the other mistake to get bigger.
Mhm.
So it's a real trade-off. You have to decide what's worse. So the theory is you just look at the problem. You say, does this matter if I'm wrong? If it doesn't matter, then you'd normally pick a 0.05 alpha. That's the normal value. Okay, but if you're designing, let's say you're attaching you're attaching wings on airplanes. And believe me, people test the bolts when they come up with a batch of bolts that they're going to put on planes. Someone's testing these bolts. Okay, probably the manufacturer, but I promise you, these bolts are rated at a certain level. Okay, and the idea is how much force that bolt can take before it snaps. Okay, now the claim is that the bolt can handle this much strength, but no more. Okay, as a left-tailed test, the force has got to be less than this number. Okay, if it goes over, you're going to break a bolt. Okay, so the claim is that the force should be less than this, and you pick your level of significance. And let's say the bolts pass the test. Okay, so we agree, we've rejected the null hypothesis. What if it turns out the null hypothesis is actually true? I'm not doing this very well. Look, the bottom line is, let's just say, yeah, I'm getting confused. Let's just say that the type 1 error means you've said the bolt is safe when it's not. And the type 2 error is saying the bolt is not safe when it is. You have to decide which one's worse. Got it? Saying a bolt is safe when it's not is a much worse mistake. Okay, so there are scenarios where scientists test things where they can be life and death situations. And if it's not that, it could be people lose their money. It could be just something bad. And scientists do this kind of stuff all the time because products have to be safe. Research has to be accurate. Tests have to be accurate. Medical tests have to be accurate. So the point is, you look at these mistakes, that in some situations, especially when you're doing research that involves health or safety or people's well-being in general, or animals, it doesn't have to be people, right? One mistake can be worse than another. And in those cases, you'd look at the two mistakes and you choose your alpha accordingly. So if the type 1 error is worse, since the probability of the type 1 error under the assumption the null hypothesis is true. By the way, if the null hypothesis is not true, you can't commit a type 1 error. Because remember, the type 1 error is rejecting the null hypothesis when it's true. So you can only commit a type 1 error when it's true. Okay. So alpha is the probability of a type 1 error. If that's a really bad mistake, you should pick a smaller value for alpha. So if the type 1 error is worse, pick a small alpha. That would be like a 0.01-ish. I'll say ish, because I don't want to tell you which one. Okay, if the type 2 error is worse, we would pick a larger alpha. And again, I'll just say 0.05-ish. Okay, but I've seen, and it's also a matter of, well, how significant does it need to be? When vaccines were being tested for Ebola, that was back during the last small little epidemic. Compared to what we're dealing with now. When the vaccines were being tested for Ebola, they weren't requiring much for statistical significance. So I've heard of medical testing where they did a 0.10 alpha because it was one of these things where the disease was so bad and people were dying so fast, it didn't matter. If you couldn't hit a 0.05, maybe you could hit a 0.10. And maybe the patient would be fine with that kind of thing if it's a kind of an experimental medication. And that stuff like that happens all the time, where people kind of agree to take things that aren't necessarily proven yet. With it, and that just means they're lowering their requirement for statistical significance. All right, well, we need to take a break here, so I'm going to just zoom out on this, and let's go ahead and come back at 10:20, and we'll get back into the material.
That was great, thanks.
You bet. Okay, so we're going to start section 7.5 now. And this is the first time when we're actually going to do a hypothesis test that allows us to compare two groups. Normally the groups are the same people, which has its drawbacks, but it also has some real cool benefits. If the individuals are the same in each group, then that eliminates a lot of possible confounding issues. If you test a group before you give them a treatment, then you give the treatment, and then after whatever time you test them again, you can't argue that one group that maybe they did better because it was a healthier group. It's just the same people. So a lot of these issues of confounding where there are alternate explanations can be eliminated when you're comparing a group against itself. There's a lot of times when you can't do that. When we were testing COVID vaccines, we the scientists definitely had to use different people. One group of people with vaccines, another group of people with placebos. These can't be the same people, right? And then they just kind of watch who gets the infections. They have to be different groups, but when they can be the same group, it's kind of convenient. And then we're working with what are called matched pair samples. So let's go ahead and jump on in here. It says in this lesson, we begin to test claims that compare means from two samples. The easiest way to compare two means is when the samples are paired. So again, we'll call them matched pair samples. This is when, oops, there is a natural one-to-one pairing between the samples which include the same kind of measurements. I'll say same type of measurements. So you could be measuring like weights, how much something weighs before and after a treatment. They'd have to be both be weights though. Okay, so the advantage is since both groups tend to contain the same individuals, many confounding questions are resolved. Remember, the goal in an experiment is for the groups to be as similar as possible. And the disadvantage, of course, is that many experiments need just different groups of people or different groups of individuals. Because of the nature of the treatment. So it just depends on what you're doing. If you're trying to see how smoking affects people, well, you have to compare non-smokers against smokers. You can't, I mean, I guess you could do before and after. You could do the same people before they start smoking and then measure those people again after they start smoking, but it would have to be years and years later. And if you're doing 20 years later, then the groups aren't really the same anymore. So because they're 20 years older. So I think that makes sense. I hope that makes sense. So let's go ahead and look at an example here. It says Prozac is a drug which is meant to elevate the moods of people who suffer from depression. In the following sample, and looks like, did I make this up? No, I've actually got data here. Mood levels were recorded before and after taking Prozac. In these values, a higher score means less depressed. We label before at Prozac values as X and after Prozac values as Y. Okay, what we don't really care about these individual scores, what we want to know is how much they change. So it's 2 samples, but we're actually just going to subtract each before minus the after to find out what the change is. And so this question down here says, what are we interested in? The differences is what we're testing on this one. Okay, differences that will be before minus after to see how much people change. Okay, so we have to compute all of these differences just to measure the changes. Some of them will be negative. That's a good thing when it's negative, because if the after is bigger than the before, that means the patient has improved. Okay, so we need to get D bar, which is the mean of the differences. Let's just say the D's differences. Okay. We'll need an S, standard deviation, SD, which is standard deviation. It's a sample standard deviation of the differences. N is the number of pairs. Which needs to be greater than 30, or the population of differences should be normal. So this is the same as the t-test we did in the last section. Okay. So just do x minus y on all of this. So 3 minus 5 is -2. That's a good thing. That means that the mood went up. Okay, 0 minus 1, also negative. 6 minus 5, that person actually got worse. 7 minus 7, no change for this person. 4 minus 10, huge improvement. 3 minus 9, same improvement. 2 minus 7, -5, still really good. 1 minus 11 is -10. 4 minus 8 is -4. So most people did get better. Some of them seem to have really gotten better. Any questions here? At this point, we need the mean and standard deviation. This is just like the last test where you need a mean and a standard deviation. We're just labeling them differently. Okay, so the number of pairs are 1, 2, 3, 4, 5, 6, 7, 8. I think there's 9 pairs here, so I'll say n is 9. And then I'm going to pop over to Desmos real quick. Let's see if I can get a page open here. Okay, so let me get into Desmos. And I'm just going to make a list of numbers. It's been a long time since we've done this, but you say A equals, and you put it in square brackets. So make sure you put the negatives in as negative. I guess I could have called this D, right, for differences. I wonder if it'll let me. Okay, so -1. I'm just going to type them all in. Okay, so I made a mistake somewhere. Let's see if I can find it. Oops. Okay, so it's a 9-element list, and I'll just double check my numbers here. It's good. So we need the mean of the D. So you just say mean of D and standard deviation STDEV of D, just like that. So we have a mean and a standard deviation. Is there any question about that? That's just like our X bar and our S, but we're calling them D bar and S sub D. Okay, so the D bar is -3. I'll say 3.67. Standard deviation, strangely, is exactly 3.5. And any questions about Desmos? Okay, so then back to the notes. So I've copied in those statistics. The next thing we do here is we're going to set up our claims. We need a null hypothesis and an alternative hypothesis. It's a little confusing because there's a couple of means, right? There's a mean mood level before you went on the treatment, and then there's a mean mood level after you go on the treatment. We hope there's a change. This is actually a test about that the mean difference indicates the patient's got better. Okay. So again, we've got the notation here. There's going to be a mu1, and it says above that's the mean of the x values, but it's the before mean generally. Mu2 is the mean of the y values. Also, everyone's favorite Pokemon. That's the after mean. Always have to say that when I cover this because I think it's funny. Mu d is the mean difference. This will just be mu1 minus mu2. Okay, now your null hypothesis is going to relate mu1 and mu2. So the null hypothesis will just say that the treatment didn't work. Mu1 equals mu2, there's no effect. It didn't work. People had the same depression levels before as afterward. Any question about that? And that's always going to be our null hypothesis. Now, what this means is that the mean difference is 0. So if mu1 is equal to mu2, then that means mu d, which is mu1 minus mu2. If those are the same, then the mean difference is 0. Okay, any questions there? The alternative hypothesis, you've got a choice. Mu1 is less than, greater than, or not equal to mu2. What do you guys think? If the treatment works, should mu1 be less than or greater than mu2? Remember, mu1 is the mean before the treatment. So should it be less than, greater than, if the treatment works?
Would it be less than?
Yes. We would hope that before they go on Prozac, the mean after is greater, which would be the mean before is less. That would mean the treatment works. Okay, any questions? Now, our test statistics, pretty straightforward. Before we would do X bar, now I'm going to erase this, just a warning, minus mu over S divided by the square root of n. And that is the test statistic. But notationally, we're doing a test on differences. So instead of an X bar, we'll use the mean, which we call D bar, because we're trying to test to see if there's a difference on average. And the mean difference would be mu sub D. Standard deviation of difference is S sub D. So the only thing is we just put some D's in here, but it's the same hypothesis test as the last one. Okay, so our D bar was negative 3.67. Mu D, if you look at the null hypothesis here, it says mu D is 0, and we always assume the null hypothesis is true. So we're going to put in a 0 right there. Okay, so mu D is 0 based on the null hypothesis, and that won't change. I think there's one problem in the homework that says on average people lost 10 pounds. So you're claiming that the mean difference is 10. And you'll see that in the homework, but that's the only time when you don't put in a 0. It's perfectly reasonable for someone to say that the change is this many pounds on average. You wouldn't say it's no change, you'd say there is a change. Okay. Standard deviation 3.5. And it's over the square root of 9. Okay, so let's see if you guys can agree on that one. Ooh. And a couple places after the decimal will be fine.
Negative 1.98.
I think I must have done something wrong. Let me see. Hmm. Oh, dang. Do we have
Oh wait,
agreement
I
on
think I
that?
got it wrong. Wait, let me fix this.
Okay.
Negative
One of us does.
3.15, negative 3.15.
That's more like what I got. Yeah, negative 3.15. Sorry about that. That's a lot of standard errors of difference. It's a really small sample size. So it's hard to prove stuff. You'll see the p-value is going to be actually not that small. It's going to be small enough though, I think. It won't be as small as 3 standard errors would indicate, but it's just this small sample size makes it hard to prove stuff. Okay, any questions about this? Okay, so we have to do a critical value now. So this is table A2. We've used it lots of times. Okay, so for degrees of freedom, because we're doing a t statistic here, t's always have degrees of freedom. That's n minus 1. So 9 minus 1 is 8 degrees of freedom. Okay, so df go down to n minus 1, which will be 8 this time. I don't know what our alpha is, so we got to go back and check somewhere. I don't see it anywhere. Is this a mistake? Okay, so I'm going to make it up right now. My alpha is 0.05. Okay, so this is just, what do I say? Alpha was not given. So we'll choose the standard 0.05. And it's my intention always to make sure I give you guys an alpha so you don't generally have to pick it. It makes my life chaotic on a test, especially if I don't give you an alpha value. Because everybody gets a different answer. Okay, and then so we can look that up real quick. Should be one tail. I did not put that down. Let's put that down. Okay, so I'm going to A2, 0.05 one tail. And 8 degrees of freedom. Does anybody need any further guidance with this? So 1.860 standard errors will be considered statistically significant on this one. So that's actually pretty easy.
Yeah, so why did we choose to do one tail again here?
Yeah, the only time you do 2 tails is when you have a not equal in the alternative hypothesis. So I'll show you that again. Is everybody okay with the table use here? I'll resolve the one tail issue in just a sec. Okay, so let's go to that real quick. I'm going to slide back up to the beginning of today. See if I can find it here. That's 7.3. We started with 7.4, which is this one. Just look at this right here. Whenever your alternative hypothesis has a not equal, those are the only time you do a two-tailed test. Okay. Otherwise, less than points to the left, greater than points to the right, and that's just the rule. Okay, is that clear?
Do we have this in this question?
Every hypothesis test will have an alternative hypothesis. So we better have. So I'm going to pop up and see if I can find it. So we, on this question, said our null hypothesis is always an equal. And here we did left. Okay, so we could add to this now that this is a left tail test.
Did the question tell us to do that, or did we choose to do it?
It is your job to figure it out. It is in the question, but sometimes it's a little less obvious. Okay, all the question says. Now, you don't want to randomly make that up. If it's not stated, then the problem is not written well. Okay, all that it says is maybe it doesn't. Oh God, I just said the problem wasn't written well, didn't I? I apologize, but it says Prozac is meant to elevate the moods of people. That's all we've got here. Okay. So maybe it should be more obvious than that. I don't remember who is this asking the question?
It's me, Parham.
Parham, hey, do you follow me here? Elevating the moods means something's getting bigger.
So shouldn't we do more than instead of less?
Now, wait. This is where it gets tricky. Which one should be elevated, the before or the after?
After.
Good. So now you're saying that the before should be less.
Yes.
That's why it's a left tail test.
Okay. Yeah, that makes sense now.
But this was really subtle. I did not make it clear in the question. On an exam, I think it's my job to make sure it's absolutely clear. Okay. So I think all of the problems will be more clear than what we just did. Okay, so regardless, let's get back. This is a one-tailed test. And does anybody remember what the test statistic was? Did anybody write that down? Sorry, the critical value?
1.860.
Thank you so much. Okay, so this is what's required for statistical significance, but do remember this one was a left tail test. So technically what you want to do is make this negative. Okay, that's our critical value. And the area of the tail here is alpha. I'll just remind you again. This one's a left tail test. Okay, any questions? Okay, table A3. Remember, we have a test statistic column, and we have a degree of freedom column, or row, I guess I should say. I think we said there's 8 degrees of freedom here. And our t statistic was negative 3.15, which we're going to round to negative 3.2. Okay, so this is the t was negative 3.15, and we're rounding here. Okay, so we'll get that real quick. In my beautiful table A3, it's negative, so we got to go to the negative part of the table. Ugh. Okay, so the negative 3.2 and 8 degrees of freedom. So I think there it is. 0.0063. Any questions about that one? That's really small. So that's highly significant, actually. So it seems like the Prozac is, for this data, indicates a significant increase in mood level. Okay, any questions about that? So I can put in 0.0063. Oops. Again, this is not as precise as we'd like. We do not double this. I guess I can draw a little picture here. This is a one-tailed test, so we do not double it. Okay, so we have negative 3.15. P-value is 0.0063. Okay. Any questions? Okay, so
Sorry, I had one question.
yeah.
So you would only double the value if it was a two-tailed test then?
Yes, agreed.
Okay, and then
Yeah, you're saying p-value is the probability of going in at least as extreme as this t statistic. So at least as extreme as negative 3.15. On a left-tailed test, this is the probability. But on a two-tailed test, you're saying it could go at least as extreme in either direction. And that doubles the probability. So you have to double the area of the tail.
gotcha. Okay.
Just on a two-tailed test.
Okay.
Okay, anybody have questions? If there's two ways to do it, then it's going to be twice as probable.
Thank you.
Yeah. Any other questions? Okay, so that's about it. This is just like the last one. Make a conclusion. If the p-value is less than the level of significance, we reject the null hypothesis in favor of the alternative. That paragraph is copied and pasted throughout the rest of the semester because there's one rule. Okay. So, by the way, before I go there though, let's double check on, well, no, I'll go ahead and write this and I'll double check afterwards. So here, the p-val is 0.0063, which is less than 0.05, which is the value that I pulled out for alpha out of thin air. Okay. It's less, so that means we reject the null hypothesis this time and support HA. Just reminding ourselves, HA said that the mean before treatment is lower than the mean after treatment, which is exactly what we were hoping the treatment would do. So we would say, yeah, that the data do support our claim here. That Prozac is effective in elevating mood for depression. I'll say, I'll put the on average here. Individuals will vary some, but for patients or for people with depression. Something I didn't mention is that these probabilities of, I talked about the probability of a type 2 error. I said it's a really complicated probability. But one of the things that lowers the probability of a type 2 error is increasing your sample size. So we've made a conclusion here, but these, you know, it's a less reliable conclusion than it would have been with a larger sample size. So the best way to improve the quality of a statistical test is by increasing the sample size. Small tests are less reliable. So people would look at this with 9 people in it, and it wouldn't mean much until it was expanded probably to thousands of people. Okay, but it's obviously if there's 9 people, it's easier to do in a classroom environment. But I don't want you to get the sense that a study with 9 people is a good study. Okay, any questions? But this is how it's done, and that's really the point.
What could you say if you did a study with 9 people and you had like an extremely low p-value?
I would say this is a very promising result that needs to be followed up with more research. So one of the other things that I've never mentioned is the notion of any treatment that gets studied with an initial study like this always has to have this replication thing. So it needs to be reproducible by some independent group. That's a standard in science. And the other thing that's a standard in science is something they call peer review. So when you finally get to publish your work in the Journal of Medicine, you know, the New England Journal of Medicine or some other journal that's reputable, it's not going to get published if your peers, and I don't mean your pals, I mean other people in your field that know what you're talking about, they have to review the study. If it becomes a peer-reviewed study, then you've got all these people that are saying, yep, this was done well. Without peer review, you've really got it's just one study. And as we've said repeatedly, data can mislead you sometimes, and people sometimes cut corners. And so, you know, there's the built-in sort of protections from bad conclusions are replication and peer review. So, you know, this is one little teeny study that would not prove anything to the FDA other than maybe opening the door for more research. Okay. Let's wrap that one up.